Okay, this is a continuation of chapter 16. We've been talking about solutions in chapter 16. You know, there's a solute dissolved in a solvent. And we've been talking about how to measure the concentration and what factors affect solubility and things like that. Okay, one of the other things that we need to talk about here is what happens to a solution's properties. We talked about this actually in chapter 15, right? Be a few sections before this. We talked about in chapter 15 the difference between a suspension and a colloid and a solution, right? And a suspension and a colloid both were heterogeneous mixtures, and a solution was a homogeneous mixture. And there were some other differences, but one of the differences between those then is that solutions, since they dissolve in the solvent, they change the properties of the solvent. If you dissolve salt in water, water no longer boils at 100 degrees. Water no longer freezes at 0 degrees. It changes that water, okay? So solutions' properties change because of what's dissolved in them. Now, if there's nothing dissolved, if you just simply mix something into water like sand, it doesn't change it, right? That's a suspension. It doesn't change the properties of the water. But if you make a solution by dissolving something into that solvent, the solvent's properties change. We call that colligative properties, all right? So when the properties of a solvent change when a solute is dissolved in it. And so we say that the colligative properties of a solution are the properties that depend on how much solute is dissolved in them. It doesn't depend on what you're dissolving, just how much. Okay? So anytime you dissolve anything in a solvent, the solvent's properties are going to change. Now, what properties are we talking about? Well, there's three main ones that we're concerned with that are going to come up, okay? One of them is all about vapor pressure. Now, we have to go back and we have to remember a little bit about vapor pressure. So vapor pressure is the pressure of the evaporated liquid above the existing liquid, right? So if you take a glass of water and you just set it on your kitchen counter and you let it sit there, let's say for a few days, obviously the level of the water in that glass is going to drop. Why? Because the water in it evaporates slowly, but it does. Now, if you were to put a lid or something over the top of that glass of water, the water would still want to evaporate, but the water wouldn't be able to escape out into the air. The water vapor wouldn't be able to escape out into the air, so it would build up in that container. That pressure that builds up is called the vapor pressure. Right? We've talked about this a little bit before, so I mention it again. If you have solute particles that are dissolved in that solvent, the vapor pressure of that liquid, of that solvent, is actually going to drop. Right? And here's a little way to visualize it. Okay? So the picture there on the left, is a picture of just the pure solvent without anything dissolved in it. So let's say that that's water, okay? Because that's what usually our solvent is in most cases. So let's say we had a glass of water like you see there, and we put a lid on top. Just like I mentioned before, some of those water molecules want to evaporate and turn into a gas. And so they go off into that little area above the liquid, and they start bouncing around, but they build up, right? There's a vapor pressure that builds up in there. But look at the picture on the right. The picture on the right is the same water from the left, the same solvent, let's say. But now something's been dissolved in there. It just happens to turn it green in this picture, but it doesn't really matter. There's something that's been dissolved into that solvent. And since it dissolves, remember, like dissolves like, so that means that there's an attraction there. So those little solvent particles, let's say they're water, so those little water molecules that you see that are blue in that picture are attracted to the solute particles that are green in that picture. Since they're attracted to them, they don't want to leave. They stay in the liquid because they're attracted. They don't want to leave, and so the vapor pressure goes down. Okay? So you have less vapor pressure, you have less evaporation when you dissolve something in that water. A real life example. Oceans are salty, right? Maybe you've been there, maybe you've been in an ocean, maybe you've tasted the water, or you've just heard about it, but oceans are salty water. Now, if you were to take oceans and measure how much evaporation happens off of oceans versus, let's say, some kind of fresh water like Lake Michigan. Lake Michigan has a lot less stuff dissolved in it than the ocean does. Well, guess what? Lake Michigan evaporates a lot quicker. There's a lot more evaporation that occurs off of that water because it's closer to a pure water than the ocean is. Okay? Right. Something that goes along with that is boiling point. This is something we haven't really talked about much before, but we need to get into this just a little bit. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid is the same as the surrounding pressure. Okay? Now, that's sometimes a little bit hard to kind of understand. So again, let's visualize this. And I don't have a picture already drawn, so I'm going to draw a picture again. Be nice, don't judge so much. So here's my water. Okay? So let's say that I took, I put this over a Bunsen burner. Okay, I don't know, I'm going to draw a flame here. Okay, so here's my Bunsen burner, right? And it's heating up my water in my beaker. Now, as these little water molecules in here start moving around faster and faster and faster, right? Because they're being heated up, and heat causes the little atoms and molecules to move faster. As they move faster, they'll be able to break away from each other easier and then go off into the air, right? So the evaporation of the water starts to happen more and more and more and more and faster and faster and faster until you get to the point where all the water molecules all want to leave at the same time. When that happens, you've reached boiling. Now, we always think that boiling is just a temperature. We're just like, oh yeah, water boils at 100 degrees Celsius. Well, guess what? That isn't necessarily true. The temperature is totally based on the amount of pressure that's on top of that liquid. So let's say that we were doing this experiment here that I've drawn really crudely. Let's say we're doing this in a regular standard room, like at your house, okay? If we were doing this at your house, the pressure that is on this water in here, the air pressure in your house, is probably about 1 atmosphere of pressure, okay? There's 1 atmosphere of pressure of the air pushing down on that water. Okay. So not only does the water molecules have to get away from each other, they have to break the attractions from each other, but they have to break through that pressure of the air pushing on them. So it takes a lot of heat to get that water to boil. But when we do, the vapor pressure, the amount of pressure that the little particles coming off of this back up, when it boils, that vapor pressure and that atmospheric pressure are actually going to be exactly the same. So when the vapor pressure of the liquid that's trying to turn into a gas equals the amount of pressure that's already pushing down from the gas that's out there, that's when the liquid can boil. Now, let's say that your house was actually on the top of Mount Everest. Weird place to build a house. I don't know why you did this. But let's say that you lived on the top of Mount Everest. The air pressure on the top of Mount Everest is way lower than it is at your house right now. I promise you that. When you go up really high in the atmosphere, the pressure drops. Well, if there's a lot less pressure pushing down on the liquid, then you don't need as much vapor pressure going back up, which means you don't need as much heat. The boiling point of water on the top of Mount Everest is like, I don't know, like 79 degrees Celsius or something like that. It's way lower than 100. Okay, way lower. So if boiling point depends on vapor pressure, and we just said on the slide before this, we just said that vapor pressure is lowered when you dissolve something in the water, well then that means that boiling point is going to have to get even higher to get the vapor pressure up to match the atmospheric pressure, the surrounding pressure. So in the end, what this all means, right, is that since a solution is a liquid that has something dissolved in it, it's no longer pure, the boiling point's no longer going to be the same. You need more energy. You need more heat to make that solvent, let's say water in this case, let's make that water molecules move fast enough to boil. So they're already attracted to all of that solute that you dissolved in there. The vapor pressure has gone down. They don't want to evaporate as much. If they don't want to evaporate as much, they certainly don't want to boil as easily either. So the boiling point ends up having to go even higher. So if you took salt water at your house, right, the water by itself with nothing in it boiled at 100 degrees at your house. But now if you took some salt and put it in the water, you're going to have to get it even higher than 100 degrees to get that water to boil. So boiling point elevation is a property of a solution. It's a colligative property. It means that the boiling point of a solution is going to be higher than the boiling point of the pure solvent was originally. So here's an example of that, right? Pure water has a boiling point of 100 degrees Celsius normally, and really, I don't even have that up there, but that's really an important point, okay? Under standard pressure, okay? You are on the top of Mount Everest, it wouldn't be 100 to begin with. But under standard pressure, it's 100 degrees Celsius. But let's say we made a 1 molar salt solution. Remember what molarity means. That means how many moles of solute there are in a liter of the solution. So 1 molar salt solution means I took 1 mole of salt for every liter of solution. It would have a boiling point that's higher. It's 100.5 something. Okay. Now I know it's not a lot higher. You're like, well, that's not much higher. Yeah, but it is higher. And obviously, if you put more salt in, it would go even higher than that. So then the big question is, why would you put salt in water when you're boiling water for cooking? Besides taste, right? I want you to think about that for a second based on what we just talked about. What do you use boiling water for when you cook? To make pasta, right? Or rice, or something like that, where you have to have boiling water and you put the noodles or you put the rice or something like that in the water while it's boiling, and that softens up the rice or it softens up the pasta so you can eat it. So that's what we use the boiling water for. Well, what's the highest temperature boiling water can normally get to if it's just pure water? Well, it'll be 100 degrees, right? That's the hottest that water would ever get, because once it reaches 100 degrees, it boils, it turns into steam, and it goes off into the rest of your kitchen, and you'll never get it again. You can't use it. So the highest temperature that liquid water could ever get is 100 degrees. But if you put salt in that water, the temperature of that water when it boils has to be higher than 100 degrees. So now you can cook at a higher temperature. Now you'd have to put a lot. You notice that 1 molar salt solution only went up, what, a half degree? So if you want the temperature to be much higher than 100, you'd have to put a whole bunch of salt into your water when you're cooking it with it. But most people don't do that. So most of the time when people put salt in the water, the only thing they're doing is they're putting it in there for taste. Okay, that's what most people are doing it for. But technically, if you had really, really, really salty water, the temperature of that water would be much higher than 100 degrees when you're cooking with it. All right, and the very last colligative property we're going to talk about is freezing point, right? We know what freezing means, right? Freezing means you're taking the liquid and turning it into a solid. So freezing point is just the temperature at which the liquid turns to a solid. Now what is that for water? Again, under normal conditions, it's 0 degrees Celsius, right? That's where water freezes, is at 0 degrees Celsius. So it turns out that if you dissolve something in water, that solution now has a freezing point that's actually lower than it normally is. To get salt water, for instance, to freeze, you would need to get the water lower than 0. Okay? So that's what we call freezing point depression. The temperature difference between the solution's freezing point and the freezing point of the pure solid. So let's go back to this idea. Right, let's go back to this idea of what water looks like when you freeze it. If you remember, when we set the water up freezing, here's a little water molecule, right? This is the O, this is the H, this is the H. Okay, so this end is partially negative, this end is partially positive, this end is partially positive. If I put another water molecule nearby, okay, this is going to be attracted to the O because it's negative, and this is positive. Those are the hydrogen bonds, right? Well, it turns out that when water lines up as a solid, as ice, right, all the little water molecules all line up in this little hexagon way, right? We saw this earlier in chapter 15. Okay, this is the way that water molecules look. They all line up nice and neat in a pattern. It happens to be a hexagon pattern, but it's a pattern. So if I were to put salt in there, okay, so now here's an Na positive ion, or here's a Cl negative ion. Well, now this water molecule is attracted to that, and this water molecule is attracted to that, and suddenly they're going to break out of their formation. Well, the only way that you get to freeze something is to put it in the formation, right? The water molecules have to line up in those hexagons to freeze. So if there are salt ions dissolved in that water, it's harder to get them to line up, right? It's kind of like if you were in charge of a bunch of kindergartners, and right before you wanted the kindergartners to line up to all go to the bathroom, you know how you had to do when you were in elementary school and you all had to line up and be nice and straight lines, all that kind of stuff. If you had given them all a whole bunch of candy right before you wanted them to all line up, good luck, right? They're all going to be all over the place. You're not going to get them to line up very easily. So water gets harder to freeze when there's stuff dissolved in it. That's what we mean by freezing point depression, okay? Pure water has a freezing point of 0 degrees, but a 1 molar saltwater solution, right? Look what happens to the freezing point. It's now down to negative 3.72 degrees Celsius. And again, if we made it even more concentrated, this would go even lower. So we go back to this big question then. Why do you put salt on ice in the wintertime? You know, and if you got ice and snow on your sidewalk or on your driveway or on the streets, and the big trucks come by and they put salt on the ice and the snow, why do they do that? Well, again, think about it. If you had ice that was all lined up in their nice hexagon pattern, okay, and this is what was all over your sidewalk or your driveway or your street, and suddenly somebody takes some salt, right, and they spread it out onto that ice, suddenly these little water molecules are really interested in that salt, and they're going to break out and go after that salt. And suddenly the ice is going to melt, because it melts when that little shape, that formation breaks down. That's what happens with any solid. When the shape breaks down, then you no longer have a solid. And so it will melt, okay? Unless it's really, really cold, right? If it's colder than this, and you only put 1 molar worth of salt on the ice, then that's the temperature it'll freeze now. If you put more salt than that, it's going to freeze at an even lower temperature. So these are what we call the colligative properties. It's one of the really important things that we know about solutions that changes the solvent when you dissolve something in them. All right? Okay, that's it for this part.